faithfully conveying value and interpreting great books worldwide. Hi there. This is Sally's Book Talk. Today we're diving into The Viral Storm with the subtitle, How to Tackle the Next Pandemic Outbreak. We're living in a time of new viral pandemics. Oh, from Ebola in the 70s, HIV in the 80s, to bird flu and swine flu in the early 2000s, and now COVID-19 sweeping the world, we're always under the shadow of viruses. Every news report on a new outbreak sparks fresh fear and doubt. Imagine a virologist who can break down the origins, evolution, spread, prediction, and prevention of viruses in an easy-to-understand way that would be hugely educational. Luckily, we've got The Viral Storm right here. The author is Dr. Nathan Wolfe, a famous American virologist. Dr. Wolfe is a visiting professor at Stanford in human biology, and he's a top expert in spotting and stopping epidemics early in the U.S. He started Global Viral, a famous research group, gives TED Talks, and Time magazine listed him among the world's top 100 influencers. Dr. Wolfe will guide us through jungles, over plains, and into cities on a virus hunting adventure. The author tackles three key questions. First up, how do viruses spread? Second, why are we hit by so many outbreaks these days? Third, what steps can we take to stop epidemics in the future? All right, first off, how do viruses spread? Oh, viruses were discovered under 150 years back. Credit to Martinus Beijerinck, a Dutch botanist, who found an infectious liquid while looking into tobacco disease. This is Philip, and he called it virus, because in Latin, that means poisonous liquid. But later, when they studied polio in foot and mouth, they found out viruses are actually particles. But we'll get to that later. Viruses are microbes, the tiniest life we know. Bacteria are microbes too, made of cells with walls like plants, but viruses have no cells and are way smaller. And if we scale the human body to the size of a stadium, a typical bacterium would be like a soccer ball on the field, and a virus is just a hexagonal pattern on that ball. Viruses have a very simple structure. To survive, they must infect life forms based on cells, meaning infecting other organisms is their fate. Thus, the ever-present viruses become the most widespread life form on Earth. Viruses are everywhere, on land, in the ocean, deep underground, and on humans. There are even 250 million virus particles per milliliter of seawater. Humans have discovered most animal and plant species on Earth. However, we still know very little about this vast group of life, viruses. Current research has only scratched the surface. Viruses might be the last new frontier in exploring unknown life on Earth. So, how do viruses spread? By observing the behavior of our close relatives, chimpanzees, we might gain some insights. Scientists like the famous British primatologist Jane Goodall have discovered through research that chimpanzees, like early humans, hunt for food. One of the hunting targets for chimpanzees is the red colobus monkey, which also belongs to primates. Oh, chimpanzees brutally hunt and eat red colobus monkeys, and viruses from the monkeys enter chimpanzees through openings and wounds. This likely happened to our direct ancestors 8 million years ago. The human immunodeficiency virus, or HIV, traces back to chimpanzees preying on monkeys. The human immunodeficiency virus originated from two monkey species in Central Africa, the red-capped mangabey and the greater spot-nosed monkey. They've coexisted with a virus variant called simian immunodeficiency virus for millions of years. They also share a common trait. They're both hunted by chimpanzees. When chimpanzees prey on both monkey species, the two virus variants enter chimpanzees through blood and wounds. At some point, genetic recombination occurred, creating a new hybrid virus that spread among chimpanzees. And so, finally, in the 20th century, a hunter in Central Africa, while hunting chimpanzees, had a wound that contacted chimpanzee bodily fluids, and the virus jumped from chimpanzees to humans. That's the origin of AIDS. So why are humans so vulnerable to viruses? The first reason lies in the evolution of the human microbiome, tracing back to our ancestors. During the transition period from forest to grassland living, unable to adapt quickly to the new environment, human populations experienced a drastic decline known as a population bottleneck. When such population bottlenecks occur, microbial diversity within species also decreases. This is because microbial infections can be acute or chronic. Acute infections kill hosts directly or trigger immunity, requiring large host populations. If hosts decrease, they struggle to survive. Chronic infections survive better in small host groups, but still face high extinction during bottlenecks. This microbial reduction is called microbial purification. Additionally, humans using fire to cook food greatly reduced microbial exposure. So what impact has microbial evolution had on us? As our microbiome became less diverse, natural selection pressure eased, causing us to lose protective disease prevention mechanisms. But with the recent population explosion, increased human-wildlife interactions have opened the viral reservoir stored in wild primates. Diseases absent from humans for millions of years may reinfect us. The microbial library preserved in our ape cousins during human microbial evolution is primed for the next viral storm. Another reason for viral spread is human domestication. Each domesticated animal carried unique microbes before taming. During early domestication, close contact transmitted their microbes to humans. Such contact includes raising, protection, companionship, and consumption, sometimes reaching extreme levels. For example, some indigenous women in Papua New Guinea breastfeed piglets. Domestic animals also act as microbial bridges, transferring infections from wildlife to humans. Nipah virus is one such example. This deadly virus emerged in Malaysia in 1999. Research shows Nipah virus first spread from bats to pigs, then from pigs to humans. Oh, bats carrying Nipah ate mangoes near pig farms, contaminating pig feed with their droppings. The virus spread rapidly in pig pens, then infected humans through pigs. Domestication also has a third impact. It increased human mobility. Livestock supply and trade created roads connecting villages, forming larger permanent communities. This created conditions for previously short-lived acute viruses to survive permanently in humans. After understanding how viruses spread, let's return to the second question. Why do humans suffer so many pandemics now? First, what is a pandemic? The English word pandemic comes from Greek, meaning all people. Actually, the Greek literal definition is inaccurate since no virus can infect everyone. The author defines a pandemic as a new infectious agent affecting individuals across all continents. So how do pandemics emerge? Dr. Wolf and his colleague Jared Diamond, American biogeographer and author of Guns, Germs, and Steel, developed a 5-level classification system. An infectious agent transitions from exclusively infecting animals to spreading globally among humans. There's a transitional process in between. In the 5-level system explanation, Level 1 agents only infect animals. Level 2 only transmits from animals to humans. Level 3 transmits from animals to humans and allows limited human-to-human transmission. Level 4 agents achieve multiple cycles of human-to-human transmission.
At level 5, the agent transmits exclusively between humans.
There are over 5,000 mammal species, but only one human species. Thus, level 1 agents vastly outnumber level 5, forming a pyramid shape. When an agent reaches level 3, able to transmit between people, it begins moving toward pandemic status. An unknown disease outbreak in August 2007 in the Democratic Republic of Congo, later identified as an Ebola variant, proved Ebola is a level 3 disease. It can spread between people to a limited extent, and monkeypox, also at level 3, shows a trend of jumping to level 4. Oh, every additional case means a greater chance for the virus to upgrade or mutate. That's why we need to closely monitor this virus. Smallpox, however, is a true level 5 agent. Viruses at this level reside solely in humans while causing massive deaths. Fortunately, humans have eradicated smallpox. Now, after a pandemic emerges, what factors boost its spread? Every major advancement in transportation changes how populations connect, impacting new microbial spread. Smallpox's impact on the New World is the classic example. During European colonization, smallpox brought by ships to the New World killed up to 90% of Aztec, Maya, and Inca populations. Beyond ships used since the age of exploration, today's roads, railways, and air travel provide new routes for moving humans, animals, and microbes. The transportation revolution enabled a quantum leap in microbial spread efficiency. Scientists found HIV dates back to 1900. If it existed in early 20th century populations and became endemic in Kinshasa, Congo by 1959, then why wasn't it recognized as a pandemic until the 1980s?
What special circumstances caused this rapid spread in the mid-20th century?
We found steamboat services, starting in 1892, in Central African forests, connected scattered populations for the first time. Viruses that couldn't survive in isolated local groups now reach developing urban centers. Chances of bodily fluid contact between once isolated carriers and others greatly increased. Meanwhile, railways built by colonists in Central Africa provided larger host populations for spreading viruses. Commercial flights starting in the 1960s completely changed pandemic transmission dynamics. Air travel's speed means even microbes with short incubation periods can spread globally effectively. These transportation methods together created an interconnected world. For pathogens once scattered and dormant, this essentially became a giant microbial mixer. This reality has permanently changed how pandemics affect humanity, truly ushering us into the pandemic era. Beyond transportation advances, medical technology has also built new bridges for viral spread. Blood transfusion, transplantation, and injections, while crucial health technologies, fundamentally accelerate pandemic emergence and spread. Medical tech strengthens human microbe connections. One clearest example is blood usage. In the past, direct contact with others' blood was rare. The same applied between humans and animals, except during hunting. Everything changed since the first blood transfusion in the 15th century. Now, about 80 million blood units are collected worldwide annually. When blood moves from one person to another, viruses and microbes hitchhike into the new host. Transfusions can transmit HIV, hepatitis B and C, parasites like malaria, plasmodium, and trypanosomiasis. Blood products also pose risks. A 60-year-old with type A hemophilia might need clotting factor equivalent to 7,500 doses. That means exposure to microbes from potentially 2.5 million people. Though don't panic too much. Today, blood banks screen for common viruses, and animal blood for consumption gets heated to kill pathogens. Organ transplantation is an even more significant biological event. Since transplants involve moving blood and tissues, microbes within tissues enter recipients. Corneal transplants have transmitted rabies. Rabies had no human-to-human transmission record. A German woman got malaria despite never visiting tropical regions. The cause? Her transplanted liver came from a Cameroonian donor. And there's another major issue. Due to the shortage of transplant organs, doctors have turned to animals, known as xenotransplantation. The author studied 160 patient samples who received pig tissue transplants.
He found signs that pig cells survived in 15% of patients, lasting up to 8 years post-transplant.
This creates ideal conditions for viruses carried by pigs, like porcine endogenous retrovirus, to cross species into humans and reemerge. To save one life at the cost of potentially sparking a new pandemic for humanity, is it worth it? The third medical way viruses spread is through injections, for tattoos, infusions, or vaccines, where poorly sterilized needles play a big role in transmitting microbes. Oh, the widespread use of needles, like blood transfusions, gives microbes a new path to spread everywhere. Medical technology helps us fight some of the deadliest diseases. At the same time, it connects humans, building strong biological bonds between people. This intimacy is unique among Earth's life forms, fundamentally changing our relationship with microbes. Beyond transportation and medical tech, bioterrorism and lab leaks of microbes bring new risks to humans. Terror groups are very likely to have microbial weapons, since microbes are easier to make than chemical or nuclear arms, and unlike them, microbes spread on their own. This viral spread is unmatched by deadly sarin gas or radioactive bombs. Meanwhile, lethal microbes can multiply in biological labs. Researchers discovered that a 1977 pandemic affecting the Soviet Union and Northeast Asia involved a virus almost identical to one from over 20 years earlier. But that virus hadn't resurfaced since that outbreak decades ago. A convincing explanation is that a lab-preserved strain accidentally infected a worker. Then it spread from there. The frequency of these microbial threats, bioterrorism, and lab errors affecting humans will increase. But at least the biggest threat we face still comes from new microbes in nature. On February 21, 2003, at a Hong Kong hotel in Kowloon, a man fell ill with severe acute respiratory syndrome and infected at least 16 others. Those 16 then dispersed to Europe, Asia, and North America, infecting hundreds. This was the origin of SARS, or severe acute respiratory syndrome. We now know SARS originated in wild bats, possibly transmitted to civets before ending up on that guest's dinner plate. High population density, large livestock production, close wildlife interactions. Combine these with an extensive, efficient transport network, and we clearly see where pandemics are heading globally. This convergence of multiple factors creates ideal conditions for new diseases in many regions worldwide. In Africa, another pattern quietly emerges. Urbanization, deforestation, road building, and wildlife consumption combine to create perfect conditions for disease emergence, even in seemingly remote areas. In hidden corners of Central African forests, the author found traces of the global H1N1 pandemic. Various local viruses and global strains are already moving along roads toward the outside world. Having explored pandemic origins and spread, the third question naturally arises: what can we do to prevent future pandemics? How can we track deadly viruses and control them? The answer partly lies in modern pandemic surveillance networks. The author and his team are developing a surveillance system. This system could detect and contain new pandemics before people even know they exist. The system design was inspired by security agencies preventing terrorist incidents. Intelligence agencies monitor potential threats, especially by reviewing emails, calls, and chat room messages from key targets. They track signal frequencies to understand patterns of terrorist activity. Inspired by this, the author suggests treating hunters in African tribes as sentinels, monitoring targets. These individuals have extremely high exposure rates to microbes carried by nearby animals. The first research step is establishing observation points and collecting samples in these isolated villages. The author set up a functional lab in Yaoundé, Cameroon's capital, specifically to analyze samples from 17 rural monitoring sites across the country. In this lab, researchers not only analyze samples to study viral diversity, but also observe how locals interact with wildlife. People engaged in hunting are on the front lines of animal-to-human virus transmission. They could serve as sentinels, allowing us to monitor potential viral threats. Through this Sentinel program, multiple new foamy viruses and 2 novel human T lymphotropic viruses were discovered. This proves the monitoring plan is feasible and effective. Expanding the system from African jungles globally requires modern medical testing and IT. One new medical technology is polymerase chain reaction. Polymerase chain reaction, or PCR, helps identify a microbe's family based on tiny genetic fragments. More effective DNA microarray chips are now widely used in labs worldwide. They help rapidly identify microbes causing new pandemics. New information technology provides complementary research tools to medical testing. In fact, such tech tools are right in your pocket. Via electronic health records, people worldwide can report health issues using mobile phones. This data not only provides timely treatment for patients, but also enables faster detection of health anomalies when analyzing large user datasets. These technologies have proven powerful during the COVID-19 pandemic. Mobile communication big data enables real-time monitoring of infection exposure, helping CDC pinpoint risk areas and close contacts. Meanwhile, through centralizing nucleic acid test data and self-reported temperature monitoring and antigen test results, we've set up an effective monitoring and rapid response system for pandemic control. In the fast-growing field of digital surveillance, mobile phones aren't the only solution. Personal online search patterns also give us info on infectious diseases. With huge search data saved by engines, people can build a system to predict disease trends. Just by searching on Google or Baidu, we might spot early signs of an epidemic brewing in a community. Social network growth also gives us another big data set, similar to Google. By watching flu trends on Twitter using keywords, people found this trend highly matches government flu prediction research, suggesting we can look at more data sources. And the evolving epidemic geographic info system now includes key layers: people's locations, their concerns, the microbes they carry, where they're headed, and who they contact. Over time, data from different outbreaks can be combined for analysis, letting us weigh factors in real pandemics, optimize all tech tools, and max out prediction power. In the near future, by merging results from remote virus labs with mobile search patterns and social networks, we'll build a true global immune system. Surprisingly, viruses can also help us prevent infectious diseases. Most vaccines we use today are actually viruses or parts of viruses. Some vaccines, like smallpox vaccine, use the link between cowpox and smallpox. Injecting a safe cowpox dose builds immunity to smallpox, fending off deadlier diseases. Other vaccines, like oral polio and measles, mumps, rubella combo, are live attenuated vaccines. Flu vaccines are inactivated virus shots, while hepatitis B and HPV vaccines use selected virus parts. Almost all modern vaccinology fights poison with poison. Some safe viruses are our best allies in fighting deadly ones. Someday, how we protect ourselves might depend on symbiotic microbes, not eliminating them. The author warns us that a big barrier to predicting and preventing future pandemics is the belief they're random and uncontrollable, which is wrong. Viewpoint: predicting and preventing pandemics isn't easy, but there's much we can do now, and new tech will help us do more. Another issue is the public can't accurately assess risks. Helping the public understand and interpret pandemic info properly is key to prevention and control. Pandemic information is a vital part of pandemic prevention and control. Media bombards us with reports on biological threats, like crying wolf repeatedly, lowering public alertness. The only way to break this deadlock is for everyone to understand risks, evaluate disease differences, and take appropriate actions. We're in an era where new pandemics rage. Fortunately, we're also in an era where tech can build a global immune system. In one, we should and can do better at predicting and preventing pandemics. Someday, we'll perfect pandemic prediction and prevention until we can call it humanity's last pandemic. By then, we'll be amazed to find our ability to detect and stop pandemics is so strong that we won't even need the word pandemic. This book, The Viral Storm, is interpreted for you. That's all for now. Reading notes are below the audio. See you next time.